Okay, we'll get started. The topic we're going to try to finish today is Blackwell PVT, and this is the Blackwell PVT table is probably the most commonly used PVT model for describing oil and gas and in petroleum engineering. So it's important to try to get a kind of handle on what it is. And so we started by talking about the Blackwell PVT properties for an oil phase. So we're interested in the properties of an oil phase at some pressure and temperature, okay, in the production system. It could be in the reservoir, in which case it's at the reservoir temperature, or it could be as the oil or the production is going up through the production pipe to the surface, in which the temperature and the pressure could be changing. Or it could actually be describing the oil and gas flowing in a pipeline system where the pressure and temperature are quite a bit lower, traditionally lower, but both pressure and temperature are changing along the flow lines, the gathering lines at the surface for the gas and the oil. So it's used in all of these types of engineering calculations: reservoir, production, transportation. Okay? And the idea is that you have an oil and gas either by itself, okay, which it probably is undersaturated, or if it's together, gas and oil together, or in any point in the system, then the gas and oil are saturated. So if gas and oil together, they're saturated. If gas is by itself somewhere in the system, it's very likely undersaturated, although it could be at its dew point, right? It could be saturated at its dew point. If an oil is by itself, then likely it's undersaturated, but it could be at its bubble point, in which case we would formally define it as being saturated. Okay? So we've got this map, and we've covered on Tuesday the oil phase, saturated, and we almost finished the discussion of the undersaturated properties. So let's just review what are the properties, the Blackwell properties of the oil phase. As a function of pressure for the saturated system, in other words, if the oil is saturated, that is, the pressure, by definition, is at its bubble point. Okay? Okay? So if I say the BO, the saturated BO is 2, okay, at 4,000 psi on the exam, everybody wakes up, okay, if I say the saturated formation volume factor of oil is 2.0 at 4,000 psi, okay, and some temperature. What is the bubble point of that oil? And then you're going to say, he said it was saturated oil, therefore the pressure, 4,000 psi, must be its bubble point pressure. Okay? So, if it's saturated, then the pressure we're talking about in the table that you have is a function of pressure. That means that the oil formation volume factor, or the oil viscosity, is the property at that particular oil's bubble point. Okay? Now, in the table, there will be some maximum, and this really should be written PBI. It's just the maximum pressure in this table, and I'm going to put this as PBI. What it really is the maximum pressure in the saturated table. Typically, that maximum pressure in the saturated table will be the highest expected bubble point of any oil in your system. Okay? So if it's at reservoir temperature, this is for a given temperature, it's constant, we have a given table. And we can have a different PVT table for each temperature. Okay? So each of these saturated tables is going to have a maximum pressure. And that maximum pressure will be the expected maximum bubble point you have for that system. Okay? So that's what I mean by this PBI. Okay? Now, it's a little outside the scope of this course, but we may create saturated black oil tables that exceed the bubble point of the highest bubble point in your system. It has to do with solving these equations in the reservoir, in the production pipe, or in the surface. Basically, is a solution of a set of equations numerically. Okay, it's a numeric. Nobody does this analytically. So you're solving these equations numerically, and one of the questions each time you solve, you discretize the reservoir, you discretize the pipe, or you discretize the flow line into small pieces. Okay, like pieces of Lego. And for each Lego, each piece of the calculation you make, you don't know. All you know is what the system composition is. Okay, which is the total GOR. The total GOR is the composition of your mixture in a black oil formulation. Because the total GOR gives you the total amount of surface gas divided by the total amount of surface oil. That's a ratio. But given the ratio, you can actually calculate the fractions, mass and mole, if you actually wanted to. So the total gas oil ratio in that Lego piece tells you the composition of the system. So the first thing it has to find out, is it one phase or two phase? Okay? If it's one phase, and let's say it's oil, then you need the properties. Okay? So you need to know, is the pressure in that little element larger than the bubble point pressure, or at the bubble point pressure? So you have to know, you have to orient yourself. So we're going to talk more about how you use a black oil table. But sometimes what you think is the highest bubble point in your system, because fluids are flowing around, ends up not being the highest bubble point in your system. Okay? Because sometimes, gas flows where it shouldn't and starts mixing with oil, and all of a sudden your gas oil ratio gets too high in a particular element of the system, and all of a sudden what you thought was the highest gas oil ratio oil is not. You've got more gas. Okay? And so you don't really always know what is the highest saturated pressure for your system, without you understanding exactly why. You just don't always know. So sometimes we'll create this table to saturation conditions, bubble points and dew points, that are higher than in reality what we think is the initial highest. Okay? And basically this is our max saturation pressure. So the point is that in that saturated table, the one thing you know for sure is that the pressure given in the table is the bubble point of that oil. Okay? That you know for sure. That's guaranteed. The composition of that oil, is given by RS. Okay? What is composition? It's the surface gas amount and the surface oil amount. Okay? And we deal in volumes. And if you know the ratio, then you kind of know the amounts of each. Okay? So the RS gives us the ratio of the surface gas volume to the surface oil volume. And that's essentially giving us, like, it's kind of a, it's not really molar, so I can't call it molar composition, but that's basically what it's giving us. But it's giving to us that in kind of a volume, on a volume basis. Okay? So it doesn't sum to 1. It's not like volume fractions or something. But you're knowing, in a sense, how much of each component you have. That's the gas-oil ratio. So that's our composition variable. And then the property BO and viscosity, which should be down here, are given. Okay? Now, the change in BO and MUO is being caused by two things changing. Okay? As you lower the pressure in this table, two things are changing. The pressure is changing, and the composition of the oil is changing. Okay? Two things are changing. And that's why the viscosity of the oil is changing, for two reasons. Okay? Now, why did the viscosity increase as we lowered the pressure? Remember? Huh? Because you're losing this light component, methane and ethane, the light components. And the light components, when put into an oil, will tend to lower its density and lower its viscosity. It's just intuition. Okay? So the viscosity is going to be increasing because the oil is becoming heavier. It's got less gas, less of the light components in solution. So that oil viscosity is going to be increasing. The oil formation volume factor you don't really have a relationship with yet, but it will be decreasing. Okay? And we showed kind of pictures of that. We showed. Okay, so that's basically, I think, the keys that are related to saturated black oil PVT properties. We also saw that the BO was essentially a straight line linear function of RS. Okay? It's always going to be that way. I promise you. Okay? It's one of the few things I can promise. Well, there's always going to be an exception, and you'll get me on that. But I've never seen it yet, so you're going to have to live a long time to find it. Now, on the undersaturated property of an oil, the first thing you have to know if an oil is undersaturated is you have to know the pressure and you have to know its bubble point, right? To know that it's undersaturated. So the first thing is that if you have undersaturated property, you know the RS, okay? Let's say you've got a piece of pipe. You know that the gas-oil ratio in that piece of pipe coming from the right, it came in, and you know that by material balance that this piece of pipe has 1,000 standard cubic feet per stock tank barrel gas-oil ratio in that piece of pipe. Okay? 1,000 cubic feet per barrel in this piece of pipe. So I go into the saturated table and I say, with 1,000 GOR, RS, value of 1,000, what is the bubble point? Okay? And it says 3,000 psi. Okay? So you go in with the RS, you go into the saturated curve up here, you go in at the value of, this is getting messy. I go into the 1,000 cubic feet per barrel here, and I find the pressure, that's the bubble point pressure, 3,000 psi. Okay? Now, it so happens that the pressure in that piece of pipe, we're solving for that pressure in the flow calculation, but we think it's 4,000 psi. Okay? Our first guess is 4,000 psi. So what we do is that we say that pressure is above the bubble point. So now it's undersaturated. We need the property, the BO and the viscosity. Why do we need the BO? We know it's RS, 1,000. We know the pressure, 4,000. What do we need in engineering calculations? Huh? We know that we need the viscosity and we need the density, right? All of our flow calculations, Darcy, pipe flow, everything has density in it. So we need density because the pipe might be going like that, right? So you've got a little bit of elevation there. So Newton's working for us or against us. We need the mass density. To get the mass density, we gave this equation here. We talked about this was the last thing. That's equal to the surface oil density of the, I'm just going to write it this way, plus the surface gas density. We did a material balance, and we found out that this was the equation. If we want density of oil at pressure, we just go in and we basically said these two numbers here, these are two constants. There's two of them, two numbers. So we can get, if we know the BO, we know the RS. The RS is always known everywhere in our system by a material balance. It's accounting, okay? You could go down to the accounting school and become an accountant, and then you would be able to do the material balance, okay? You just keep track of stuff, okay? You start with 1 billion barrels, you don't lose any of the barrels. That's the accounting. It's either in the reservoir, it's in the pipeline, it's somewhere in the system. We don't lose barrels. We don't lose standard cubic feet. It's a conservation of volumes. That's the model. So we always know the GOR everywhere. And we have some estimate of the pressure. So we have to find out for that GOR, what's its saturation pressure? Is that higher or lower than the pressure itself? That means it's either one phase or two phase. And if it's single phase oil and it's undersaturated or saturated, we can use this equation. This applies to both saturated and undersaturated. Both. The RS we know kind of by material balance. The BO we go into these tables looking for. Okay. Now the undersaturated properties, we know the GOR, we go in and find out what's its saturation pressure, we find out if the pressure is greater than that bubble point, then we need to use this table, okay? So for each oil up here in the saturated table, for each oil that you have there, there's a bunch of different oils. Each oil's got a different composition. We need to have properties BO and MUO at pressures above its bubble point. That's the undersaturated table, okay? So these are going to be BO and MUO are going to be given. I probably should have written this a little bit differently. These are going to be given for a series of pressures greater than that bubble point of this particular oil. And likewise the BO. It's going to be given for pressures greater than its bubble point. Okay? And there might be 3 values or 10 values or 16 values, whatever. There's going to be a number of values at different pressures, at least one. Okay? For a specified RS value, for a specified bubble point. Yeah.
So the first input is the RS, and then you decide whether it's saturated and undersaturated based on the pressure.
Yeah, that's how to use the Blackwell table. We'll come back to that a little bit towards the end of the session today. But yeah. But in finding whether you have undersaturated oil, you have to first know the GOR. You have to see that that GOR is within the range of RS values in the saturated table, 1,000 cubic feet per barrel. Because you remember our original yesterday, in the example, it was 200 cubic meters per cubic meter. Sorry about that. Times 5, that's 1,200 or whatever. I know it's 1,000, but it's a little bit more. Okay. So that GOR that we have has to be within the range of the RS values. If it's within that range, okay, it means that it's going to be an oil. Okay, and then you have to find its bubble point. You find that from the table up here. And then once you see that the pressure you think you have in your system is above that, we need this table. Okay? Likewise for the viscosity. Now I'm gonna sketch this. All of this blah blah word stuff, it's not easy to see. But let's go back to the plot of the BO and the RS curves. Okay? And I'm going to try to give a little bit of curvature like that. And then I'm going to try to be fancy here and copy that because it's got the same shape, right? Yeah, that's pretty good. It's going to look like that. Okay. So these are the values that were in our table. Okay. So this is our saturated table. I'm going to change, okay, so, and let's put some numbers here. I think from yesterday we had in standard cubic meters per standard cubic meter, we had 200 here, right? And I had 2 here, and the units here were cubic meter per standard cubic meter. Okay, 1 and 0, something like that, right? And I think this pressure down here I put was 300 bar. Okay, so we're back to Tuesday. Now, let's say that somewhere in our system, and because these tables are specifically for reservoir pressure, I'm sorry, at reservoir conditions, reservoir temperature, okay, in our system, and this has to be at the reservoir temperature, okay? So it's somewhere in our reservoir. Let's say that we have a GOR equal to 200. Okay? Probably it's equal to 200 everywhere. Okay? From top to bottom. So we go in with that value of GOR. And we see that the bubble point of that is, my goodness, Curtis, been drinking. 300 bar. Okay? So we see that the bubble point for an RS equal to the GOR of 200, that's equal to 300 bar.
It's a saturated case, so we will have a gas phase and an oil phase.
We're not there yet. We haven't said what is our system pressure. Okay, we haven't talked about what is our system pressure.
So this GOR is the total GOR of the system.
I'm just saying that we went somewhere in the reservoir, we pulled the sample out, okay, and we measured the GOR was 200. Okay, that's all I'm saying. Now I'm saying that the pressure where we pulled that oil out, the pressure in the reservoir where our system is 320 bar. Okay? It's 320 bar where I took that oil. I want to make calculations in my reservoir model at 320 bar for this particular oil. It might be, for example, at the water-oil contact. It could be Whitson Oil Company, I guess. So water-oil contact. Okay? And we need to know the viscosity of that oil down there where there's water, because water is going to start moving in, displacing the oil, and Buckley-Leverett, the Darcy equation, says that the ratio of the viscosity of oil to the viscosity of water is very important as to how fast the water and where the water moves in. Okay? So we need the viscosity of the oil. So this pressure of our system, where we're interested, is greater than the bubble point, therefore undersaturated. Okay? Okay. I'm told you that we needed the viscosity, so I'm going to have to come down here and give you the viscosities. Okay? So this is the viscosity, goes up, except the same pressures. Okay, so the viscosity curve is going to look something like this. The saturated curve. But we want the viscosity at 320 bar, so that's not on that curve. So what we do is that we need the property of this oil that has a 300 bar bubble point, a gas oil ratio of 200 cubic meters per cubic meter, and we need to take that oil to 320 bar and measure its viscosity. And when we do that, we're going to get a viscosity that's higher. Okay? And the BO value is going to drop. Like that. But maybe your estimate of the water oil contact is wrong, and maybe it's down at deeper, and the pressure is 340 bar. Okay? Or maybe you've got oil below the water oil contact. There's fields like in Saudi Arabia that's got more oil below the water oil contact than we have in our biggest field in Norway. Okay? And what if we want to get that oil out? Well, you need to know its viscosity. And its pressure might be 360 bar, way down there. I don't know. So you need these properties for this particular oil. You might need them it does get a little bit flatter here. So, okay, and the oil viscosity can look something like that. And what we said is that the undersaturated properties are only changing for one reason, and that's what? The pressure is changing. The composition is fixed. It's got this 200 cubic meter per cubic meter GOR, and we usually draw this over here like this. So for the undersaturated, that particular oil has a constant GOR, a constant RS, along this, where these properties are being measured or calculated. So along here, RS is constant. Equal to 200. Okay? That's why we need the properties. We need the viscosity and we need the density down there to make calculations. Are there any questions about this? This is the undersaturated oil properties. But that's only for that 200 GOR oil. Now let's look at another case, which is common, particularly in the North Sea, actually pretty much everywhere. And I'm just going to say many reservoirs have an initial variation, vertical variation, of RS versus depth, true vertical depth. Okay? Why is that? Again, our friend Newton, gravity. You guys know the pop artist. I promised to play some music during the break. I'm going to play some Norwegian music during the break. But there's a rapping artist, Eminem. I'm sure most of you have heard of Eminem, right? Okay, and he talks about gravity, right? One of his songs talks about gravity. Well, again, because of gravity, we end up with most reservoirs having a solution gas-oil ratio we call it RS because it's solution gas-oil ratio versus depth that decreases. Okay, just why? Because methane being lighter tends to go up, and the heavy components, C30 plus, tend to go down. It's that simple. Okay? So let's say that this was our 200 cubic meter per cubic meter oil. So it ends up that down at the water oil contact, it's not 200, but it's 150 standard cubic meters per standard cubic meter at 320 bar. Now we need the undersaturated property of a of an oil with an RS of 150. But we don't have that in our table up here. The 150 RS is here. I don't know, what would be 150 is here. Okay, it's right there. So if we go into here, its bubble point is 270. Okay? So the first thing we find is that the bubble point is 270. And we get that from the saturated RS pressure curve, right? That's where we get that. We go in at 150. This is at the water oil contact. We got the bubble point pressure. And now we can go in and we're looking for the BO, and that's going to be here. I have to mark it in green. Okay, that's our 270 value. And the BO is there. But we don't want the saturated 270 bar bubble point viscosity or BO. We want it at 320. So now we're going to have to come up with this curve, which will look something like that. It'll be a little bit flatter. Okay, it's less compressible. Why is it less compressible? Because some of the light components are gone, right? There's less light components. So it's more compressible, and that makes this flatter. The viscosity is going to be changing something like that. So now we can go in at 320 bar and find viscosity 320 bar here. That's at the water oil contact. And the BO is here at the water oil contact. So we've got the viscosity and the BO. That's what we need to make engineering calculations. And we need the BO because we need density. Okay? There's other reasons too, but for sure for density. So in reality, for every saturated oil we have in the original table, we need the undersaturated set of properties. Okay, so in reality, when we create this table, we need this curve, like that. We need that curve. We need that curve. We need that curve. We need that curve. Okay?
Can we say, are they more or less parallel?
No, they're not parallel because the slope of this is reflecting the compressibility of the oil. Compressibility of the oil is lower if you have more gas in solution, right? It's a lighter oil. So the slope of these are getting flatter and flatter as you have less and less oil in solution, gas in solution. And likewise for the oil, you have to have all of these curves for the oil viscosity. For each saturated oil, you need the undersaturated curve. Okay? A set of numbers. Okay? So the undersaturated tables is kind of a set of tables. It's a set of tables. There's a little table for each oil that you had up here in that saturated table. So if you got 10 saturated pressures, then you need 10 little tables in the undersaturated part of the table. Okay? This is one of the subsets for the lowest RS value. Now, if we just, as an example, we take this lowest value here, along here, the RS value for this lowest value here, this is maybe, I don't know, 40 bar. I'm sorry, I'm sure, at 40 bar, let's say this is, sorry, 50 bar, maybe that's the lowest table value. Let's say the GOR is 40. That's the lowest one. That's the one up here. So along this line, the GOR is constant at 40. Okay? Okay. If anybody feels like they understand everything completely without any doubt, then something's wrong with you. Okay? Unless you've been working with this before. Okay? You have to be confused. It is confusing, a little bit. Okay? But the point is this. This is the life you've chosen. You're sitting in this room because you wanted to become a petroleum engineer, okay, and get paid lots of money and on and on and on and on. This is what you have to live with, like it or not, okay? And it's one of the main responsibilities I have in teaching you this course is that you understand this, because this is how you get the properties: density, viscosity, single phase, two phase, and that all affects the calculations in the reservoir and the pipe and then in the flow lines, okay? So you're just going to have to buckle down and figure it out. Try to really understand it, like it or not. No matter how confused you are now, try to get unconfused. That's your job, okay?
Curtis,
Yeah,
how are you generating these lines?
okay.
Drawing them, like,
Yeah, so what we're going to talk about, the mechanism of doing that, the mechanism of doing that we're going to talk about at the end, okay? Okay. Okay. So that's basically we've kind of exhausted the discussion of oil phase black oil PVT. We know the properties. We know there's two tables. The first saturated table is a single table. Okay. The second undersaturated is a set of N subtables. Okay. For each subtable, it is for a particular oil. That particular oil is defined in the saturated table. Okay? Yeah.
What about temperature? Or is that because temperature doesn't change that much, you usually have one table?
No. For every new temperature, you're going to have a whole new big table. Okay? Whole new big table. So if you got 4 reservoirs you're producing from, each one at a different temperature, then you're going to have 4 of these big tables. And we're only halfway through it. Okay, we only got the oil side now. Okay? We're going to have to get the gas side. And then if you're in a flow line, okay, you might have 4 or 5 temperatures from reservoir to the surface flowing temperature. All right.